Happy Monday, yes. Only the people at City College know that it's Monday. Everyone else thinks it's Thursday. Where's everyone today? 2, 4, 6, 8, 10, 12, 14. Okay, I guess I'm preaching to the converted. Today is a really bad idea to come late, today's class, because as I mentioned in the last class, today we're going to be doing math you've never seen before. And trying to learn it without hearing it in class is much, much harder than trying to learn it when you do see it in class. So congratulations, you guys showed up on time. You're the wise people. And the other people, will have trouble with it. But what can I do? Class starts at 11. Okay, so first a little bit of motivation. Again, feel free to interrupt at any point. I don't mind being interrupted. I say that every class, but I mean it. If there's something, if somehow you can't read my handwriting, hard to believe, then just ask me. If you don't understand something I'm explaining, I'll explain it again in different words. It's not a problem. Again, the goal is not for me to present as much material as possible. The goal is for you to understand what I present. And if it means me repeating things, I'll repeat it. It's not a problem. Okay, so let's start with reviewing a problem we did at least 5 times already. So if you remember, if we looked at a CSVR, A goes to B. So we did the analysis of this, and let's assume that there's a step function in CAE. So remember, we wrote out the equation for the CSVR equation. Time rate of change, in minus out, the rate of reaction. And then the initial condition was CA was its value at t equals 0. So it was a non-zero value. And generally, in most of these problems, we've assumed that this value was steady state. It didn't have to be steady state. It's whatever it was at t equals 0. So, of course, I could write the same equation for t less than 0. It's the exact same equation, but everything has a t less than 0 on it. And then when I subtract the two, I get these deviation variables, the prime variables. So dCA prime dt is CA in prime minus CA prime over tau minus K CA prime. This equation looks just like this equation. The only difference is the initial condition now by definition is 0. Because CA prime is its value minus its value at 0. At 0, it's the value at 0 minus the value at 0 by definition at 0. So the advantage of this, even in this case, is the initial condition is 0. Okay, so then what we did is we just brought all the CA primes to the other side of the equation. So I brought this term and this term to the other side of the equation. Did a little algebra and got a different time constant, t, which is tau over 1 plus k tau. Took the Laplace transform and wrote the equation this way. So this is the Laplace transform of all the left side. This is the Laplace transform of the right side. And notice I have a polynomial in S here. It's a simple polynomial. It's 1 plus st. And when I solve for CA prime, I've got CA in prime over t over tau 1 plus st. So one thing I want you to notice is I have a polynomial in the denominator. It's a simple polynomial. It's a linear polynomial, 1 plus st in S. But this polynomial came from the left side of the equation, and I divided it out. Now why is that? What's the difference between the left side of the equation and the right side of the equation? The left side of the equation came from this term, and this term. They're all things in the system, naturally in the system. Whereas the right side of the equation, CA in prime, was the perturbations of the system. So this is the side that, the driving, the thing that changed. The right side is what changed. The left side is the system itself. So if I take the CSVR and I want to change something, I want to introduce the change in the input, CAE. Or I could have introduced the change in the volumetric flow rate. Those are the 2 easiest things to change. They would sit on the right side of the equation, and everything else on the left side are things I'm not changing. I'm not changing the rate of reaction, the form. I'm not changing the outflow. I can change what comes in, but I can't change anything else. So this part, this polynomial, that came from the left side of the equation, this, is called the characteristic equation. it's characteristic because it's the stuff that isn't changing. It's the stuff that polynomial that characterizes the system. It's not that critical what it's called. I just want you to realize that this distinction between the system and the driver. This is the driver. This side has the driving stuff, drivers. In this case, it has CA in prime. I could have also had another term with a V in prime for the volumetric flow rate, would sit on the right. So that's the way we usually break it up. The driver's on the right, the system on the left. And that polynomial that sits in the denominator comes from the system. And the nice thing about that is I could do different problems where I change CA in many different ways. I change V in many different ways. And that polynomial doesn't change. Now, CA in prime can be lots of things. I could have changed it as a step function. I could change it as pulse. So if I change it this way, then if it's a step function, then I have CA prime is CA in prime. So CA prime tilde, CA in prime with no tilde, T over tau, times 1 over S, 1 plus ST. So notice there's another factor of S here, but this factor of S came from the driver, not from the system. If I have a pulse, then delta prime is 1. So I would just have CA in, a CA prime tilde is equal to the amount. So what does a pulse mean? A pulse means like I take an extra bucket of A and I dump it in at T equals 0. So nothing happens before T equals 0, nothing happens after, but at T equals 0 I take a bucket of A and I dump it in. So the amount in the bucket, I'll call B for bucket. And then I've got T over tau, 1 plus ST. So I've got delta times B would be the amount that's thrown in, where B is the amount in the bucket. And I want you to notice that I have different polynomials in the denominator. In the case of a step, when I invert, I go back to my page here. And this one we've had a number of times. 1 over S, 1 plus ST is line 5. And so this is line 5. And this gave me CA in prime, T over tau, times 1 minus e to the minus T over T. Whereas, if I have a pulse, that's not line 5. I just have 1 over 1 plus S tau, that's line 4. And in line 4, notice I have, so let's see, I've got B T over tau comes in. And 1 over 1 plus ST gives me a 1 over T times e to the minus T over T. T's cancel. And notice the difference here. When I have, and this is of course CA prime of T. This is of course for the step, and this is for the pulse. So notice physically the difference here. When I have a step change in the input, as T goes to infinity, I have CA prime. There's a difference in the steady state of CA. It gives me CA in prime, the change in CA in, times T over tau. Remember, T over tau, T is tau over 1 plus K tau. T over tau is 1 over 1 plus K tau. So at long times, a change in CA in prime, a step change, leads to a change in CA prime, even at infinite time. Because at infinite time, the 1 survives, this doesn't, and I have a change in CA in prime, gives me a long-term change in CA prime. We get a new steady state in CA. On the other hand, if I have a pulse, and this, at least in this system, at infinite time, CA prime goes to 0. So I have a pulse in CA in prime, and CA in, and that causes a change in CA, but eventually it relaxes back to where it was. because CA prime eventually goes to 0. So that's a little bit of just background. Any questions on that? Yep.
The question on the vocabulary is driving the same as the forcing function?
Yes. Driving is the same as forcing. That's usually what people call a forcing function. So the forcing is on the right. Okay. So, of course, when we do these problems with Laplace transforms, as you see, we start with our equations, we Laplace transform them, we take the characteristic polynomial and move it to the right side of the denominator on the right side of the equation, and at the end of the day, we have to get CA prime, from CA prime tilde, we have to invert some sort of equation that has a denominator that's a polynomial. And the numerator here isn't a polynomial, but it could be. I could have a complicated driving function that also gives me a polynomial here. So generally, I want to invert something that looks like n tilde of s over d tilde of s, where d tilde of s is the characteristic polynomial. And what I would, or most of d tilde of s. So d tilde of s is mostly the characteristic polynomial. And when I say mostly, I mean, because notice there was an extra s here from forcing function, because the forcing function was a step, but most of it was the characteristic polynomial. So our job generally is to invert these things. Now, we said that we don't usually use the complicated complex variables formula to do these inversions, because that inversion is a hard way to do it. Usually we use these tables with the left and the right. By the way, given how poor the attendance today, I'm going to start taking attendance. Does someone have an extra piece of paper that we can use as an attendance sheet? And the people who don't think it's important to come can just take it next year. Take the class next year. So, yeah, just sign it, write your name clearly and pass it around, make sure everyone signs it. 20. So 12 people are missing, 12 or 13 people are missing. So if they make that a habit, they'll just take the class next year. Okay, so our goal here is to do these inversions. And we're going to look at the assumption, under the assumption, we're going to start out with a simple assumption that both n tilde of s and d tilde of s are polynomials. Because in most of the problems we're going to do, they're polynomials. They don't have to be. We could have sines and cosines, but let's start with the simple case. So if we want to invert this, then how do we invert it? Well, we start, the first step is to factor the denominator. If it's a polynomial, let's factor d tilde. And that way we know what the zeros of d tilde of s is. So what does factoring mean? If this is a polynomial, that means I try to write d tilde of s as s minus s1, s minus s2, s minus sn, if it's an nth order polynomial. And some of the s's may be the same, and some of them may be different. But that's what I mean by factoring a polynomial. And this is, of course, where I make the lead coefficient 1. So s to the n is multiplied by 1, and if I have anything else, I just include it in n. So I can include the constant in n tilde, so that d tilde is a polynomial whose highest power is s to the n times 1. Okay, so now there are 3 cases we're going to look at for how to do this inversion. So I've got case A. S1, all the SIs are different. Are distinct. So we want to see how to do these inversions when the SIs are all different from each other. Case B is going to be where some SI are multiple. What does that mean? That means that the d tilde of s is equal to s minus s1, say to some power n plus 1 times s minus s2, etc. So it's a power where n is different from 0, not equal to 0. And case 3 is going to be where the SIs, say what S1 is alpha plus I omega, and S2 is alpha minus I omega. So where pairs of roots are complex conjugates. Now, the obvious question is, why do I need them complex conjugates? Shouldn't I just talk about one of them being complex, as opposed to having pairs? Well, in all the problems we're going to do with polynomials D, A0 plus A1s plus A2s squared plus A3s cubed, all the coefficients of the polynomial are real. And it's easy to prove if the coefficients of the polynomial are all real, then if I have any complex roots, they have to come in pairs of complex conjugates. Because if I didn't, when I multiplied this out, I would have coefficients that were complex. If all the coefficients of the whole polynomial are real, that means whenever I have complex roots, I have complex conjugate pairs. So that way, when they get multiplied together, all the imaginary parts cancel out. So again, you can prove that very easily. I'm not going to prove that here. That's something a little bit. I can prove that if people have a question later on, but outside the class.
I think conceptually I think something, the reason why we're doing this conversion is to break up like when you said you're going to
Yeah. I'm going to get to that. I have not to that yet. So you read my mind. That's good. That's good. You're. N is N for numerator, D for denominator. That is, in this particular case, the numerator is just a constant. But I want to allow it to be polynomial because in many examples we'll do later on, the numerator is also a polynomial. Now, in general, the numerator and the denominator might be something other than a polynomial. I'm not getting to that now. I would take a simple case where they're polynomials. Other questions? I'm starting to understand you through the math, so we're improving here. Okay, so these are the three cases, and as was just Erica, is that the name? As Erica, I actually remember some of these names. As Erica just mentioned, we're going with, a lot of times we can't find this in the table, but sometimes we can write this as a sum of terms, each one of which is in the table. So as Erica just suggested, we're going to want to break this up, figure out if it's a sum of terms, each one of which is in the table. And I want to do that breakup for three different cases. So she took the words right out of my mouth. Okay, any questions? So let's concentrate on topic one. And this is the example I did at the end of the last hour. If you remember, at the end of the last hour, I did an example, 1 over s minus a, s minus b. And I broke it up into something over s minus a plus something over s minus b. That was a very, very, very specific example. Let's look in general, and let's see what I can do. So let's let n tilde of s, so over d tilde of s, equal to, so now I factored the denominator. Here's the denominator. So I can write it as m tilde of s divided by s minus s1. That is, I can take all the other factors plus the numerator and lump them into m tilde of s. And by hypothesis, all the other s's are different from s1. So if I evaluate the numerator at s1, it's not infinity, because there's no s minus s1s in the denominator, it's finite. And what I claim is I could write this as c over s minus s1 plus some remainder or tilde of s. I could write it as a constant over s minus s1. So let's figure out what that constant is. To figure out what that constant is, let's multiply both sides of the equation by s minus s1. And I think I want to call the left side something. Let's be consistent equation? Will I give it a name? No, I'm not giving it a name. Okay, I don't have to give it a name. So to figure out what it is, let's multiply by s minus s1. So if I multiply both sides by s minus s1, I have m tilde of s is equal to c plus r tilde of s times s minus s1. And of course, yeah. And now what I'm going to do is I'm going to evaluate, so I multiply just by s minus s1. And now I'm going to evaluate at s is equal to s1. Well, at s, remember, r tilde of s, well, so at s equals to s1, this is 0. So that tells me that c is equal to m tilde of s1. And m tilde of s1 is not infinite by hypothesis. It's not infinite because it has no s minus s1s in the denominator. And this is finite. So I know what c is. So I can write n tilde of s over d tilde of s as c over s minus s1 plus r tilde of s, where this is now m tilde of s1. This is just a number. I can evaluate it. And now I can try to invert this. If I invert this, I'm inverting a constant over s minus s1. Well, I know from my table that if I have 1 over, where is it, 1 plus st, if this is f tilde of s, then this is 1 over t, 1 over tau, e to the minus t over tau. So I know that that's the inversion from my table. Correspondence. So if I have a constant over s minus s1, let me get it in this form. And the way I get it in that form is I take m tilde of s1, and let me let me factor out a 1 over minus 1 over s1, minus 1 over s1, minus s1. And then what's left in here is 1, because I think this becomes a 1, plus s over minus s1. Runs 1 over minus s1. Because when I multiply the minus s1 back in, I get the minus s1, and here I get the minus and minus equals plus s. But this thing now is exactly in that form. So when I invert this, this is just a number that comes along for the ride. M tilde of s1 divided by s1, the minus. That's just numbers. And I'm inverting this. So this is 1 over tau. Tau is now minus 1 over s1. So 1 over tau is just minus s1. Because it's 1 over this. This is 1 over that is just minus s1. Times, I ran out of space here, e to the minus t over tau. Well, t over tau is minus 1 over s1, so that gives me plus s1 tau. So maybe I should write it in the numerator. And here the s1s cancel and the minuses cancel. So this goes to m of s tilde of s1, e to the s1 t. I've just done the algebra. I just inverted this, and the inversion of n tilde of s, e tilde of s, inverse, the Gauss transform inverse of that, is equal to m1 tilde of s, 1, e to the s1 t, plus the inverse of the remainder, which I don't know anything about. So is that clear? So let's just review again. I have this n tilde over d tilde. I want to break it up into a sum of terms or sum of terms, each one of which I can find in the table. Here's something I found in the table. So the first thing is I broke it up into one term plus everything else. And this one term is a constant, which I already know what that constant is, over s minus s1. So then I plus everything else. So I'm focusing on this, and I just manipulated this into the form that I found in the table. Use the inverse, and I find the inverse of the first term is this, and then I've got everything else. Now notice everything else is just this. So I just do the same thing over and over again, one for each factor, and they all look the same. So that says if it looks like this, the inverse for case A is the sum of terms that look like this. So I get m tilde of S1 e to the S1t plus, well, then I have to break up R into the same way. So then I can't call it m. R is going to have to call it, I'll break up this into m1 over S minus, m2 over S minus S2. So I'll get an m2 over S minus S2, so that'll be e to the S2t of S2 plus dot 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 plus mn tilde of Sn e to the Snt, where I should really call this m1. m1, all the factors except for S minus S1. m2 is all the factors except for S minus S1, S minus S2. M3 is all the factors except etc. So I go on and I get all the other factors. So is that clear what we did here? Now let me do a little simple example. Let me give an example about how to find R tilde. So a simple example about how to find R tilde. So let's look at, say, I have an example here somewhere. Yeah, let's look at an example. So let's say I have S plus 3 over S minus 1, S minus 2. So let's say this is my n tilde, and this is my e tilde. Let's say that's what I want to do. So I write this, so this is n tilde. So I want to write that first as m tilde over S minus S1. Here S1 is 1 and S2 is 2. Simple example. So I write this, so I have S plus 3 over S minus 1, S minus 2 is equal to m tilde. So that's all the other factors. S plus 3 divided by S minus 2 divided by S minus 1. So the numerator is n tilde. This is n tilde. I could call it n1 tilde. Notice that when S is equal to 1, this is finite. And then I have plus R tilde. Well, let's notice, so I can write this, we claim, as m tilde of S1. So I evaluate this at S1. At S1, and S1 is, let's just get this right. Yeah, I evaluated it at S1. And S1 is equal to 1. So that's 4 over minus 1 is minus 4 over S minus 1 plus R tilde. So I evaluated this at S equal to S1. So minus 4 is M1 tilde of 1 at S1. Now, I want to calculate R tilde this. So how do I calculate R tilde this? I take this and I subtract that. So let's find remaining R tilde this. So that's S plus 3 over S minus 2, 1 over S minus 1. Times this minus 4, plus 4. So I take this and I subtract that. And they both have an S minus 1 in the denominator, so I factor that out. And this is R tilde. So let's see what that is. That's equal to 1 over S minus 1 times S plus 3 over S minus 2 plus 4S minus 2 over S minus 2. So that way I put it under one denominator. So then I get 1 over s minus 1 times 1 over s minus 2. And I have s plus 4s is 5s. Plus 3 minus 8 is minus 5. It's 1 over s minus 1, s minus 2, times 5, s minus 1. The s minus 1's cancel, and I get 5 over s minus 2. Is that clear? Okay, I want to calculate r tilde of s. How do I calculate r tilde of s? I take n tilde over d tilde, and I subtract. I take this thing, and I subtract this thing. What's left? This, so I took this thing is this, and I subtracted this, which was 4 over s minus 1. And then the rest is 9th grade algebra. It's just algebra. So I did that subtraction, and notice that there's no more, that r tilde has no s minus 1 in the denominator. It can't. That's not an accident. We knew it didn't because we assumed that there was only one factor of s minus s1 in the denominator. So it couldn't be. Had I found an s minus 1 in the denominator, I would have made a mistake. So this is r tilde of s. Invert means going from from the s domain to the t domain. That's exactly what I mean by inversion. Because in the end, we are not so interested in a solution in the s domain. We want a solution in the t domain. So that's what I mean by invert. And that's the whole point here. We're trying to take a solution in the s domain and turn it into a solution in the t domain. And so we're breaking things up into different terms in order to do that, to some terms. Good questions? Okay, let's also just notice that note n tilde of s1, we call it m1 tilde of s1. I should always call these m1 because it corresponds to s1. I think I got all the ones. Because of this, it makes sense to have the m1. Notice that m1 tilde of s1 is n tilde of s1. And notice it was m1 of s1, m1 tilde of s1. What was m1? m1 was all of n and all of d except for s minus s1. So I can get the same result by saying this is d of s, ds, at s1. I should get the same result. Well, let's verify that first to make sure that's not crazy. If this is d, and I take the derivative, I get a bunch of terms. I've got s minus s1 times everything else. So by the product rule, if I take the derivative of this whole thing, it's the derivative of s minus 1 times everything else, plus everything else times the derivative of s minus s1. Well, the first term is derivative of s minus s1 with respect to s. So that just gives me a 1, and I get everything else. That's actually what I want. Everything else evaluated at s1. That's exactly what I want. That's really what I want in the denominator. So I have to make sure that the other terms don't contribute. Well, now if I take the derivative of this thing times s minus s1, when I evaluate it at s minus s1, at s is equal to s1, this term's going to give me 0. So the only term that's going to survive the evaluation at s is equal to s1 is the derivative of this term times everything else. So therefore I get exactly what I want here. I get the right answer here. So this is a nice way to represent it. Now, why am I doing that? If I have a polynomial, it's not a problem. But if I had a more complicated d, if d were, for example, sine s, let's say d were a sine function, if d tilde of s then that's not a polynomial. However, I know that the sign is linear in S. So you might recall that the limit as S goes to 0 of sine S over S is 1. So that says that it goes to 0 linearly. So it's like a factor like this, but not exactly. And that's because if I write the Taylor series for sine of S, I get S minus S squared over 2 factorial plus S to the 4th over 4 factorial plus dot to dot. So the leading order term is linear. But of course, it's not just S minus S1. It's more complicated than that. So, but if I had something like this, I can always come up with, I could write n tilde, if I want to evaluate m1 tilde of S, that's equal to n tilde of S over sine of S, omega S, then m1 tilde of S1 would be n of S1, n tilde of S1, divided by omega cosine omega S1. So I can evaluate, because that's the derivative with respect to S evaluated at S1. So this more general formula allows me to handle more complicated functions than this. And even if I have a polynomial, and I know that the factors are different, I don't even have to go through the trouble of doing the entire factorization. If I'm only interested in the first term, I could just take the derivative of the polynomial. I could just take the derivative. If D could just be the polynomial, I don't even have to bother factoring it. I could just take the derivative of that polynomial. Any questions on that? So that's case A. And that again tells me that the Laplace transform inverse of n tilde over d tilde for case A is a sum of terms, each one of which looks like n tilde of Si over dd tilde of S ds at Si times e to the Si t by equal. So if I can break up the denominator as a product, if I can factor it this way, then the inverse just looks like this. I know exactly what that inverse is. So notice I don't have to bother calculating each individual mi. I get them immediately this way. If I know what n is and I know what d is, I'll just take the derivatives here. So it's a little easier for the calculation to do it this way. We're interested in it, again, because, for example, in this case, in any problem that we're doing, we have some time-dependent differential equation because we're interested in the time-dependent problem. So we have a differential equation. In this case, it's simple. Let's say we have 5 CSTRs in series. You really don't want to do all the algebra the way we did in the beginning of the semester for 5 CSTRs in series. So the algebra just becomes unbearable when you do it the way you did in the beginning of the semester. So what we try to do is we use Laplace transforms. We go from the time domain to the S domain. And then we have algebraic equations, not differential equations. So we do the algebra and we get a solution, Ca prime tilde, in terms of S, as just algebraic. And if I have for example, if I have 5 CSTRs in series, I'll get a 5th order polynomial benefit. You really don't, so you're not going to find a 5th order polynomial in the table. But so what you want to do, we're not interested in this, we're interested in what is the time dependence, t. So I need to go from the S domain back to the t domain, and that's called inversion. And again, since the table is only a finite length, you're not going to find every possible function there. But many times you'll find a function that if you break it up, you can break it up into a sum of functions, each one of which is there. And that's what we're learning how to do here. Speak louder, please.
why is that inverse term there?
Why is the inverse term where?
And log plus 1 inverse, right?
Yes, because this, the n tilde over d tilde, is the right side of the equation. F Ca prime tilde is some function of s. I don't want Ca prime tilde. I want Ca prime. I want Ca prime. So I want to invert Ca prime tilde.
Okay, there at the bottom you said same differential of d tilde s, the whole expression.
For d tilde, yes.
So, what was the part that you were saying, you were over there, and you were saying just this part? When at first I was following you saying, like, you were saying, like, you're splitting up the d tilde s function, and you're saying,
I factored d tilde, yes. Here's a factor. I factored it.
but for this being the whole thing, I it's something you said about like.
Okay, I factored d tilde and to find, because I wanted to find the factors, the individual roots, the zeros of d tilde. And then I went through it, I started with one of them, and I worked through it. And I noted that n1 tilde were all the factors besides s minus s1 in the denominator and all of n in the numerator. And I could go through doing it this way one at a time. But I noticed I get the same answer if I just take various derivatives of d. I get the same answer, and the algebra is easier to do it this way. That's all. Then I get the same answer. Any other questions? Okay, so I think we're done with case A, and now we're going to case B. When I write case A, I should circle the A so you know that I'm not just misspelling the word case. Case A. Case A. Okay, so now I'm in case B. Okay, any place but on top of my notes. It's all right. Okay, so what happens? Case B says I have something to a power, so it's more complicated. So if I have n tilde of s over d tilde of s, and I'm being a bit pedantic by always writing the s. When I have a tilde, it's always a function of s. So I don't have, I can just write n tilde over d tilde, because the tilde means it depends on s. So this case is n tilde of s divided by, or what we call it, n tilde of s, divided by s minus s1 to be n plus 1, and here n, assume n is greater than 2. So I have, so it's got everything else in there. And let's see, do I want to write it exactly this way? Yes, I do want to write it that way. Okay. Okay, so here the claim is that I could write, now notice here, I said I could write it as C over S minus S1 plus R tilde. Here it's a little bit more complicated. Here I'm going to write it as R tilde, there's going to be a remainder, of course, plus Cn plus 1 over S minus S1 to the n plus 1, plus Cn over S minus S1 to the n, plus dot 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 plus C1 over S minus S1. So I claim that, and notice this is a big improvement. Why was this an improvement? Because instead of this being a function, it was a constant. So when I have a constant over S minus S1, I can look that up in the table. A function over S minus S1, I can't look up in the table. So over here, instead of having a function over S minus S1 to the n plus 1, I have the sum of terms, each one of which I can look up in the table. Even though I have a bunch of terms, I can look up each one in the table. With me? Okay, so let's calculate what all these C's are. Let's find C1, C2, Cn, Cn plus 1. And the way to do that is I'm going to multiply both sides of the equation by S minus S1 to the n plus 1. So if I do that, I have m tilde of s is equal to, well, I'm going to have the r tilde of s times 1 to the n plus 1. But then I'm also going to have the Cn plus 1 plus Cn s minus s1 plus C2 s minus s1 squared plus dot 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 plus C1 s minus s1 to the n. So all I did is I multiplied by s minus s1 to the n plus 1. And now I'm going to evaluate it at s is equal to s1. I have m tilde of s1. Well, all these things that have powers of s minus s1 go to 0, and I just get Cn plus 1. So I got the first one. Now I want to take the derivative, the m tilde ds. Well, this goes away, and this becomes Cn plus derivative here is 2. What this should be Cn minus 1. And then I have 2 Cn minus 1 s minus s1 plus dot 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 plus n C1 s minus s1 the n minus 1 plus derivative plus dr tilde ds s minus s1 to the n plus 1 plus r tilde n plus 1 s minus s1 to the n. So all I did is I took the derivative here. And now when I take the derivative at s1, anything that has an s minus s1 and it disappears. So all I'm left with is this is Cn. Now I take the second derivative, d squared n tilde ds squared. And that's equal to this dies, and here I get 2 Cn minus 1 plus the next thing was 3 times 2 s minus s1 in the next term plus dot 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 plus n minus 1 s minus s1 to the n minus 2 plus what I get from here, n plus 1 n r tilde s minus s1 to the n minus 1 plus d squared r tilde s squared s minus s1 to the n plus 1. And now I evaluate this at s is equal to s1. If I evaluated s equals to s1, all those guys disappear, and I'm left with this. So I have d squared n tilde ds squared is equal to 2 Cn minus 1. Notice I have 2 there. 2 is the same as 2 factorial. This is 2 times 1. Notice here I have 3 factorial. Well, so if I continue, what I find is dn of n tilde ds to the n is equal to n factorial c of n minus 1 minus n plus 1 minus n. Do I have that right? I should use n. Let's use n. If I take n derivatives, it's n factorial. So this tells me that c sub, whichever one, c sub j. Okay, so here j is equal to n plus 1 minus n. So let's solve for n. n is equal to n plus 1 minus j. So c sub j is equal to d n plus 1 minus j of n tilde ds n plus 1 minus j divided by n plus 1 minus j factorial. So that's the formula for all these c's. So I did explicitly the first 3, and notice that here I have a 2 factorial, here I have a 1 factorial, here I have a 0 factorial. 0 factorial is 1, 1 factorial. The next one would be a 3 factorial, etc. So here I have the c's. So now I just proved that this is correct. Where is the form? This, I just proved that this is correct. And I've told you what the C's are. Here are the C's. And the way I find R tilde is the same way I did before. I just take this guy and I subtract all of these. And what's left, and then I do the high school algebra to get R tilde. I'm not going to waste your time doing that algebra. But that way you know how to do it. And now the only question left, once I figure it this way, is how do I invert each one of these? Well, that I look up in the table. If I look up in the table, if I look at I have a 1 over 1 plus s tau to the n. That's line 6. So let's note that when I have line 6, I know that 1 over 1 plus s tau to the n f tilde s gives me an f of t that is line 6. It's 1 over tau to the n times t to the n minus 1 over n minus 1 factorial times e to the minus t over t. So I know that from the table, and now I just need to get each one of these into this form. So I have terms that look like Cj over s minus s1 to the j. That's what each term looks like, where j goes from 1 to n plus 1. So let's get this into the right form. Again, I'm going to factor out, I've got a Cj, and I'm going to factor out S1 to the J minus S1 to the J. I'm going to factor that out. So then this thing, so I factor out an S1 to the J. So I have S over minus S1 to the J minus S1 over S1 to the J. Well, actually, let's do a little nicer. Okay, so I'm going to factor out a minus S1 to the J. This whole thing is to the J power. So when I put an S1 to the J in, I'm dividing each term by S1 to the J. I don't need the J, because I have the J power out there. There's no J. So let's do that nicely. So when I factor out an S1 to the J, I pull it out, and inside here, since I have the J power, I just divide by minus S1. So what does this become? This becomes Cj over minus S1 to the J times 1 plus S times 1 over minus S1. And this whole thing can be back. So it's just a little bit of algebra. And now this is in the right form, so let's do the inverse. Of this. So the constant comes along for the ride. Cj over minus S1 to the J. And now we have 1 over 1 plus S tau to the J, which is exactly the right form here. So I get, and so let's determine that tau now is 1 over minus S1. So 1 over tau is minus S1. 1 over tau is minus S1. So tau is 1 over tau is minus S1. So now I get minus S1 to the J. That's this factor. And then I get T to the n to the J minus 1. E to the minus T over tau. T over tau is E to the S1 T. And the only thing left is n minus 1 factorial, J minus 1 factorial. So notice this cancels. And what am I left with? I'm left with Cj over 1 plus S tau to the J. Cj over, where is it? Cj over S minus S1 to the J inverts to tilde S is the NFP. Inverts to exactly this, Cj over J minus 1 factorial, T to the J minus 1, E to the S1 T. So notice in case 1, the inverse looked like this. I got exponentials, I got a coefficient just turns exponentials. When I have this, it inverts to here, and when I want to invert the whole thing, that is n tilde of S over S minus S1 to the n plus 1, that inverts to, I have a sum of terms. So I've got the Laplace transform inverse of our tilde of S. But I have plus a sum of terms from 1 to n plus 1, where each term is of this form. So I've got Cj over J minus 1 factorial, T to the J minus 1, E to the S1 T, where the Cj's are exactly this. I know it's not algebra, but I want the concept to be clear. In case A, we've solved this once and for all. When it looks like case A, we have the solution once and for all. We don't have to do each case separately. Here's the solution. Where is case A? Case A. Case B, we don't have to do it every time we come across this. For case B, here is the solution once and for all. Here is the solution. And I want you to notice that in case A, I just have a sum of exponentials. Good old sum of exponentials. In case B, I have t to the power times exponentials. If you remember, when we had two CSTRs in series, where the volumes were different, we just got a sum of exponentials, because I was exactly in case A. I had T1 was different from T2. So I was in this case. However, when I was in a situation where the volumes of both CSTRs were the same, all of a sudden tau 1 was equal to tau 2, T1 was equal to T2, and I had a 1 plus ST squared. That's exactly case B. And in that case, I got a solution that was not just an exponential, it was T times an exponential. And now you can see why. It came directly from here. And this is the case where what we call resonance, where we don't just have, let's say S1 is negative. So we don't just have an exponential decay as we would in case A, because I just have the exponentials. But at first, I have t to the power. At small t, it grows before the exponential takes over and it decays. Very different behavior when I have t to the power. Questions? Okay, I'm trying to go slowly here so you get this. Usually I would do all three cases at once. I'm not going to get through the third case, but I'll get through part of it. Questions? Talk. That was the case where we have reactors in series where the volumes were the same. So that was a special resonant case that we saw. Now, when would we get something like this? One easy way of getting this is if you have 5 reactors in series, all different volumes. That's this case. You'll get, in the denominator, you'll get a 1 plus ST1, 1 plus ST2, 1 plus ST3, all of the properties. This case, you'll get, for example, if you have some of those 2 or 3 of those CSTRs with the same volume. So then I'll get 1 plus ST1 cubed with 3 of them have the same volume. So that's exactly this case. And in that case, you don't just get exponentials, the sum of exponentials times coefficients. You get a sum of coefficients times t to a power times exponentials. Notice the power starts at j minus 1. So if n is 0, then the largest value of j is 1, and therefore you don't get that. When n is 0, you're in case A. So this is case n not equal to 0 is case B. Question? Okay, so now we're ready for the complex conjugates. So let's assume that S1 is alpha plus I omega, and S2 is alpha minus I omega. And we already argued that if S1 is alpha minus I omega, there has to be an S2. Otherwise, the coefficients of d tilde wouldn't be real. And we're under the assumption that the coefficients of d tilde are real because they make something physical. Okay, so let's just notice what things are going to look like there. So let's just notice that n tilde over d tilde is equal to m tilde of s over s minus alpha plus I omega s minus alpha minus I omega. And let's just multiply that out to see what that's going to look like. So this is equal to, and I don't know why this is here talking about a blackboard, m tilde of s. Let's just multiply this out. So this is s minus alpha minus I omega, s minus alpha plus I omega. If I rewrite this as s minus alpha plus I omega times s minus alpha plus I. This one is minus I omega, this is plus I omega. So I have something minus something times that's for saying something plus that something. So we know that's just s minus alpha squared. Minus I squared omega squared. But I squared is minus 1, so I have plus omega squared. So I just multiply this thing in. And I know that this thing, because I have a root here, I just have something, and I'm assuming that there are no multiple roots. So the algebra I did here actually is the same. That is, I can do this. This algebra didn't assume that S1 was real. This could have been complex. So I know I could write it as C1 over S minus S1, where C1 is M1 tilde over S1. So I know I could write this as M1 tilde of S minus I omega over S minus I omega. This way. Plus R tilde. R1 tilde. That is, if I take S minus I omega as my, and I think I got that was S minus I omega. I know that I can just appeal to this formula. This formula says I take S minus S1 and I take M tilde over S minus S1. So I can write this as what? And of course, I can do that right. This is alpha minus I omega. Alpha minus I omega. So now I got it right. So this is S1. So I know that it's equal to the constant, which is M1 tilde and S1, divided by S minus S1. plus r tilde s. Correct? Now, that's because I decided to choose S1 as alpha minus I omega. I could have equally chosen S1 to be alpha plus I omega. So had I done it the other way, I could have said this is equal to M2 tilde of alpha plus I omega over S minus alpha plus I omega. Where this now is my new S1 plus R2 tilde. So it doesn't matter which one I call S1. Had I called this one S1, I would write it this way. Had I called this one S1, I would write it this way. Each one gives me a different remainder, where for each one, I'm appealing to this, I'm just using this formula. Is that clear what I'm doing? Is it clear what I'm doing? So that tells me that I can write n tilde over d tilde is equal to m1 tilde of alpha minus I omega over s minus alpha minus I omega plus m2 tilde of alpha minus I omega, alpha plus I omega over s minus alpha plus I omega plus some r tilde. So this is my starting point. I can essentially appeal to this formula twice to know what the coefficient of S minus 1 over S minus S1 is and 1 over S minus S2. And maybe I shouldn't use M1 and M2. Maybe I can call this M minus and M plus to not confuse with what I did before. So let's call this M plus, and this is M minus. And this is R plus, R minus, R plus. And this is just R. So that way I don't confuse you with my definition of M1 and M2 here. So is this clear, what I've done? So now what I want to do is see what I can learn from this. What can I do from all this? So I need a little bit of complex variables that I'm going to do. So this is an aside. So recall, we said the only way to define e to the ix that's consistent with what we know about exponentials for real variables, the only way, and that's something that you prove in the first day of a complex variables class. I didn't prove that here, but I could in a review session. The only way is to define this as cosine x plus I sine x. Let's follow the logic from that. So that would tell me that e to the minus ix would be equal to cosine of minus x. But the cosine is an even function. Cosine of minus x is the same thing as cosine of x. But the sine of minus x, sine is an odd function, it's just minus the sine of x. So there should be minus I sine x. So just for fun, let's add these. If I add them, I have e to the ix plus e to the minus ix is equal to, well, these cancel, and I get 2 cosine x. So that tells me immediately that another way of writing cosine x is e to the ix plus e to the minus ix over 2. Well, instead of adding, why don't we subtract? If we subtract, I get e to the ix minus e to the minus ix. The cosines cancel, and here I get a plus minus minus gives me a 2I sine x. So that tells me another way of writing sine x is e to the ix minus e to the minus ix over 2I. So these are things we're going to need to know. And this is kind of cute. We can relate sine and cosine to these funny exponentials because we know how to write the funny exponentials in terms of sine and cosine. So that's a result from complex variables that we just derived for you that we're going to need. Now, what else do we need to know from complex variables? Well, as you recall, we said that any complex number, if this is the real and the imaginary axis, we can write any complex number z, which is x plus iy. We can write it as a vector. where this is z, this is x, and this is y, where x is the real part and y is the imaginary part. And it's very common to consider something called z bar, which is the complex conjugate, which is x minus I. And geometrically, it's the reflection about the real axis. Z bar, it has the same x, but it has a minus y. So that's called the complex conjugate, Z bar. Now, so we need to prove a couple of things, which I don't have a ton of time to do. So, do you have a picture of that board? So I have 4 of them. So that's called the complex conjugate. And let's just notice, let's say I have z1 plus z2. If I take the complex conjugate of that, I claim that's equal to z1 bar plus z2 bar. Well, why is that? Because this is x1 plus iy1 plus x2 plus iy2 bar. This is z1 plus z2. So I can write this as x1 plus x2 plus iy1 plus y2 bar. And when I bar it, barring just means I turn I into minus I. So this becomes x1 plus x2 plus minus I y1 plus y2.
What's the meaning of the bar?
Bar means I reflect about the real axis. So it means I change plus I to minus I. I just change the sign on. And I can rewrite this obviously as x1 plus minus I11 plus x2 minus I12. And this is just z1 bar plus z2 bar. So I just proved this. How about z1, z2 bar, product? I claim that's equal to z1 bar, z2 bar. Again, let's go through the details of that. z1, z2 is equal to x1 plus iy1, x2 plus iy2. Let's multiply it out. That's x1, x2 plus I squared y1, y2 minus y1, y2 because I squared is minus 1 plus I times x1, y2 I times x1, y2 plus x2, y1. And now if I take z1, z2 bar, that's equal to, I just flip the sign of this, x1, x2 minus y1, y2 minus I, x1, y2 plus x2, y1. Well, let's note what z1 bar, z2 bar is. That's equal to x1 minus I, y1 times x2 minus I, y2. If I multiply this out, I get x1, x2, minus a minus is a plus, I squared is a minus y1, y2, so minus y1, y2. And then I get minus I x1, y2, minus I x1, y2, minus I y1, x2, minus I y1, x2. So these are the same. So it's exactly the same. So this is improved. These are just sort of the simple proofs that you do in basic complex variables, but we need them. And now, as a result, since I know when I add things and take the complex conjugate, I get the complex conjugate of the sum of the complex conjugates. And when I multiply things and take the complex conjugate, that's the product of the complex conjugates. So it follows that if I have a polynomial of z bar, that's equal to the complex conjugate of the polynomial of z. And I do that by induction. So if you remember, this is a proof by induction, which I'm not going to bother with right now. But you can see, where does that come from? because a polynomial is a0 plus a1z plus dot 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 plus a n z to the n. So how do I know that when I take p bar of z, that I'm going to get p of z bar? How do I know that? Well, each one of these terms is a product, so I've got a sum of terms, and I know that the bar of the sum is the sum of the bars, and each term is a product. But I know that the bar of a product is the product of the bars. So that's essentially the proof of that. And these are all things that we're going to need. So as a result, what we're going to want to prove, and I'm not going to have time to do that now, I'll have to prove next time, is we're going to prove something really cool. So we have that n plus of phi. What we're going to prove is that n plus of alpha plus I omega bar is equal to m minus of alpha minus I omega. In other words, what we're going to prove is that m plus of z bar is equal to m minus of z bar. Now, why is that interesting? I'm not going to have time to prove that now. We'll do that at the beginning of the next hour. That's going to tell me that these two numerators, their numbers, because they're evaluated somewhere, are related to each other. They're just as complex conjugates of each other. So the numbers up here are just going to be complex conjugates of each other. And that means when we do the inversion of this term and this term, when we do the inversion, remember we do inversions like this, we're going to be able to combine these two terms because the coefficients are going to be related. And this is again the coming attractions. What you're going to find is that when you combine in such a way that we're going to get sines and cosines. So that's the coming attractions. I think the end of the show, which we continue next week. That's the coming attraction.